Okay, so hi all, welcome to the last day of this very nice conference. We will begin with a talk by Nivedita from Oxford. You heard some things about her career trajectory and her research interest before, and today she will tell us some more about category theoretic methods in quantum field theory. Please.
Hello, am I audible? Yeah, okay. I would firstly want to thank the organizers, Kasia, Sumati, Sylvie, and Sujatha for organizing this thing, because I have never felt happier, more empowered. Like this entire week is like me being crying in the last night's dance performance because I was so overwhelmed, to me being like confident all the time because of so many women around me. So thank you for having me. I will try to not be too technical. I want to just give you an idea of the field. What are some of the things that I'm doing? What are some things people around me are doing? And at any point, if I use a word that you don't know the definition of, please stop me. I would just ask you to just say hello loudly instead of just raising your hand, because I might just be too into my notes or too much into the board to look at you. So just shout if you have questions. Okay, so the title is Category Theoretic Methods in Quantum Field Theory. And I'll first start by listing down a couple of places where category theory appears. So in axiomatic definition or attempts thereof. So axiomatic definitions of quantum field theory have been people's research interest all the way from 60s with Whiteman axioms, Kastler axioms, at this time, they were obviously not written in a category theoretic framework, but as time progressed, they evolved into AQFT or algebraic quantum field theory, which is pretty category theoretic. And I would also put here factorization algebras. So factorization algebras capture, suppose this is some manifold M. These are some opens in M. You would assign a vector space to each of the open, and then they satisfy some axioms. If I want to be too technical or too n-labish, I would say it is a co-presheaf on some opens, and it satisfies some descent, but I don't want to go into the definition. This is just introduction. And then there is obviously the functorial formalism, which, yeah.
What is that diagram?
So this is some space-time manifold M, U1, U2, U3 are opens in that, and factorization algebra will assign some vector space or some algebraic quantity to each of these opens, and then it will satisfy certain properties. So this is factorization algebra is the algebraic properties of these open, like vector spaces assigned to these opens. Functorial formalism, Witten, Atia, Siegel, late 80s. So here they sort of axiomatized the path integral. So I'll talk about this in a bit after I finish my list. So these are, so just if you want to do the definition of a QFT, category theory is bound to appear. Then the second place it would appear is what is called generalized symmetries. So there's a 2-week workshop at ICTS right after we finish our workshop on generalized symmetries. So this is a very new, well, very active and new research field. So the idea is that initially groups were capturing symmetries of QFT. And we want to sort of now say that categories or even higher categories give higher form symmetries. One intuition that I like to keep in mind is that group is like a very special case of a category. So it's a one object category where every morphism is an iso. And so what we have done is firstly made it multi-object and also removed the condition that we want everything to be invertible. So in that sense, categories are generalizations of groups, but much, much bigger generalizations. I'll not say much more about it, but the idea is that their symmetries and defects or topological defects are extremely closely related. So you can have, when people say they have higher form symmetries, they have, so codimension 1 all the way to point defects. So for example, this is my space-time manifold. Here is a topological defect. A defect is topological if you can move it up to ambient isotopy and the partition function doesn't change. So this is a codimension 1 defect. It's a codimension 1 submanifold. And then I can have a couple of codimension 2 defects because I'm an example to keep in mind would be in a 3D QFT, Wilson lines are codimension 2 defects. So higher symmetries come from topological defects of increasing codimensions. Okay. And a third place where it appears is if you want to study the homotopy type of the space of QFTs. So physicists are very happy to talk about the space of QFTs. They have deformations of QFTs, parts of QFTs, but mathematically, this object is absolutely sort of ambiguous. So you can say something about the homotopy type of this object. There are, in example, is the Siegel-Stolz Teichner conjecture. So this tells us something about 2D n equals 0, 1 supersymmetric quantum field theories. So the space of these things, and it relates it to something called TMF. This is an elliptic cohomology theory. This is a spectrum and it has the corresponding cohomology theory associated with it. So if you want to study the space of quantum field theories of certain kind, you are bound to land into some kind of categorical framework. There were times when physicists hated the word categories and now they're more and more happy to use it. Yes?
You're going to tell us what do you mean by this higher higher symmetries.
So I will not really spell it out, but higher symmetries are basically topological defects in your theory. So higher symmetries come from topological defects. Initially, if you just had a codimension 1 domain wall, that would give you, basically, people were only seeing the top layer of this and calling it a group, but you have more, like a lot more structure in it. And so basically higher symmetries come from higher and higher codimension defects. So I would not really go into the details of it, but it is one of my research interests. So if you are interested, I'm happy to write to you more about it. Okay, so now let me come back to the functorial definition, because that is what I want to talk about. So okay, so for a fixed space-time dimension D and a fixed geometric structure S on the manifolds, so these geometric structures can be just a smooth structure, Riemannian, conformal, spin, any kind of geometric structures that physicists are interested in. So a QFT, let's call it Q, assigns a C vector space of states to closed D-1 S structured manifolds. Okay, so some vector space of states to D-1 dimensional manifolds, and let me say, okay, and then a transition amplitude to each D-dimensional S-structured manifold with incoming. So let me give you an instance. So for example, I have so this picture is of a D-dimensional manifold. So this is D-dimensional, let's call it M. It has some incoming boundary. Let's call it N, and some outgoing boundary N prime. And I've already said that I'm assigning a vector space to codimension 1 things. So let's call these vector spaces H sub Q of N and H sub Q of N prime. So N and N prime are D-1 dimensional closed manifolds. And then Z sub Q of M. Sub Q is just saying I'm talking about the quantum field theory Q. Will give a linear map like this. So this is the transition amplitude that is associated to this manifold. Yeah?
Since you have fixed the space-time manifold, and
Yeah.
then this
I have not fixed the space-time manifold. I've fixed the space-time dimension.
okay, yes, fix the dimension, and you're
Yeah.
taking the space of all
Yeah.
space manifolds.
I'm going to make such an assignment for every closed D-1 dimensional manifold.
Okay.
And so this thing is called a cobordism, every D-dimensional cobordism.
Okay, thank you.
So I've only fixed the dimension and the geometric structure. I've not fixed the manifold.
All the geometric structure, which could be a.
No, the geometric structure is fixed, but for a given quantum field theory, it is fixed, but I'm giving you different instances of it. So if I'm talking about a Riemannian quantum field theory like Yang-Mills, I've said D to be 4 and geometric structure to be Riemannian, like everything comes equipped with a metric. So these things will have a metric and this thing will have a
Yeah,
metric.
but it could be any geometric.
Any geometric structure.
So including a Lorentzian one, for example.
It's slightly harder to set Lorentzian cobordism categories, but yes, people have attempted to do it.
Okay.
Yeah, usually this framework works really well for Euclidean things, but it is possible to set it. Like this, yeah, let me just come to it in a second. So a couple of things that this satisfies. So H sub Q of the empty set has to be equal to C. So of course, empty set will always be included in any sort of empty set can be seen as a D-1 S structured manifold, and I want to assign it to C. And it, if I have, so this is one thing, and the second thing is for a closed D-dimensional manifold, I'll say S manifold, you Z of ZQ of M belongs to C. So if I have no boundary, this is going to be a map from H of empty to H of empty, which is telling you it's a map from C to C. And any map from C to C is actually fully determined by a complex number. And this complex number is the partition function. So one test would be whenever you're trying to set up something like this, you evaluate it on trivial closed manifolds and try to match your construction to what physicists have already computed. So partition function of the theory Q on M. Okay, then there are things that this functor satisfies. So I'm going to call this, so ZQ is going to be a functor from Cobb S D-1D. I'll just spell out the details in a second. To wet. So Cobb is a category whose objects are D-1 closed S manifolds. And one morphisms are cobordisms. So for people who have heard the word cobordism for the first time, a cobordism is a D manifold such that its boundary is split into a disjoint union of incoming and outgoing. So whatever number of boundary components you have, you split it into in and out. And then, so that is basically the data of a cobordism. So a cobordism would be some manifold M such that del M equals del M in, disjoint union del M out, and the composition is gluing. So if I have something like this and something like this, and let's say something like this, I can glue them along. This is probably not a good color. Maybe I'll just make it darker. So I'll glue this along this boundary and glue this along this boundary. And so that is the composition in this direction. And vector spaces, you all know. So vector spaces, and linear maps. So there are two properties that we want to impose on this functor, or two things that I want to highlight about this functor. So number one is, what is functoriality capturing? So when I said it is a functor from this to this, functoriality says that composition here goes to composition here. And that is what is capturing locality of the path integral. So the word locality has different meanings for different physicists. But locality here means that if you have a space-time manifold, you can chop it up into, so I can chop it up here further, and I can make assignments to smaller and smaller pieces. Let's say there was even a genus here. I can make assignments to smaller pieces, and the transition amplitudes would just compose. So this is, functoriality is just capturing the locality. And two is that it's a symmetric monoidal functor. So symmetric monoidal means that if I have a disjoint union of objects, so let's say n prime disjoint, then z of n disjoint n prime would just be z of n tensored with z of n prime. This is important because, again, physics tells us that if you have disjoint systems, then the space of states should break into a tensor product. And what makes things quantum is that you have this tensor here. So if these things were Hilbert spaces, this is what makes things quantum. So if I had picked a target category to be something like Lagrangian spans or something, I would still ask for a field theory to be a symmetric monoidal functor out of cobordisms to some other category, but it captures a quantum field theory when you land in vector spaces and when you choose the tensor product on your target category to be tensor, basically, because that's what physics tells us. So symmetric monoidal landing in something which has this kind of monoidal structure, like bilinear, makes things quantum, and functorial makes things local. Any questions about the definition?
Can
Yeah.
you say something about what symmetric means?
Yes. So symmetric monoidal means that disjoint union doesn't care about n disjoint union n prime or n prime disjoint union n. And here this tensor product is also symmetric. In general, symmetric means there is an isomorphism between Zn tensor Zn prime and Zn prime tensor Zn. And this functor doesn't care about how you take the two things. There are other kinds of monoidal, just to say braided monoidal and so on. But right now we care about symmetric monoidal. Yeah.
Okay, so I was trying to get my head around the definition. So we have the functor is from the, we have considered the space of all cobordisms of t-dimensional manifolds with t-1 dimensional boundaries.
Exactly. This can be empty, by the way.
Okay, what was this ZQM? Like ZQ is the functor, right?
ZQ is a functor.
What is this you have written in the box thing? ZQM is from this one.
ZQM is a functor.
Yes.
M has to be thought of as a one morphism.
Okay.
From n to n prime, from the incoming boundary to the outgoing boundary. So functors evaluate morphisms. Yes. So Z of M is a functor from whatever the functor assigns to this guy to whatever the functor assigns to this guy. Okay. So this is an equation that is happening in the target category vector.
Okay.
This is the morphism, and this is source and target.
Right. Okay.
Is that okay?
And this vector space assignment, like in the axiomatic framework, we don't worry about like how the vector spaces are being assigned or anything.
No, you have the way the vector space will be assigned. So this, let's say, ZQ of n, where n was a d-1 manifold. This vector space depends on the theory. So the quantum field theory you're working with will tell you what vector space to assign here.
Okay.
So that is the functor you choose. Abstractly, any quantum field theory can be a functor like this, but if you pick a specific quantum field theory, it will tell you exactly what vector space to assign and what linear maps to assign.
Thank you.
So is there a link between the symmetry of the monoidal category and the functoriality in this case? So is the quantum nature, does the quantum nature relate to the locality?
So of course, you can think of this as being the gluing over the empty set. And then, of course, this will just be the tensor over C, which is essentially what is happening. So functoriality captures, in some sense, that is why some people also like to call this locality, because locality is also that disjoint systems get assigned disjoint things. But I just wanted to highlight that the fact that there's a tensor product here and not just a Cartesian monoidal structure makes things quantum. But you're right that this is just the gluing over the empty set, and this is just the tensor over the empty cobordism. And in that sense, this is also a locality equation. Okay. So now I want to, maybe I can remove this. So now I want to talk something about generalizing this definition. So this definition evolved thinking that there is a particular time direction, although things are Euclidean, but what people would like to think is that this is like a time slice and this is like the evolution. So this is space-time, but there is a clear chosen evolution. And now you can ask the question, why can't I sort of chop up my space-time further? So it turns out you can. So you can have higher cobordism categories. So just heuristically, you can go, let's try to generalize it one by one actually. So I can, let's say, start with points. So this is a point. One morphisms are just one manifolds. So if I have some set of points like this, I can have a cobordism between them. So this is some empty set here, some points here. Okay, and also I can have a circle, which is empty to empty. So this could have been the data of Cob 01, but I want to build it further up. So I can add two morphisms, and these would be so now here are the points. And there is a map between this point and this point, this and these, and there are also one morphisms down here. And this surface is thought of as a like a cobordism between these blue things. So two morphisms are two manifolds with corners. And then I can go to 3 morphisms. Although I would not, I'll just draw a picture with something that doesn't have corners. So this is a 3 manifold. So its boundary is 2 manifolds. I've made them closed here, but they don't have to be closed. And then you can go all the way to the extent that, let's say we are at n morphisms. So again, here you will recover your space-time. Okay, so what I've done is I had some space-time with some genus, and I have chopped it up in sort of d directions so that I have locality even on the level of a point. So these points here are points on these objects of the Potsdam category. And there is one other thing you can do. You can go all the way up to infinity, but after n, so n was the, let me call it d, because d was the dimension of my theory. So up to d morphisms, I have the space-time, and then I can go all the way up to infinity by adding diffeomorphisms and homotopies of diffeomorphisms and homotopies of homotopies and so on. Now you're obviously going to ask, why would you want to do this? Because it turns out that category theory above level 2 is almost intangible. To write a 3 category with all its associators and all the data of what is a 3 category, like objects, morphisms, 2 morphisms, it's too much data, like probably 60 to 80 pages of data, and it can only be done on a computer. Although people have tried to do it by hand up to 3, but 4, 5, it's already impossible. And so going to infinity sort of makes your life slightly easy again, because if you generalize all the way here, then you again get mathematical tools to define the category precisely. Otherwise, it would just be this heuristic definition. Okay, so cob D with some S structure can be made in an infinity D category. So infinity means I have all this data of homotopies all the way up to infinity, and D is so all morphisms above D are isos. So I keep the track of the morphism data up to D, and everything above that is invertible in some sense. So this can be made into this nice mathematical thing called infinity D categories. And now we want to promote that functor also to be a functor of these things. And we start running into the need for developing new maths. So we need higher categorical algebraic targets. We need to understand how can we make vect. So remember, vect was the category of vector spaces and linear maps. Firstly, there is an obvious thing that I can do. I can make it unitary, so dagger, and sort of topologize it. I'll just say continuous, make it continuous. And I get Hilb. So Hilb is the category of Hilbert spaces and bounded linear maps. So it turns out that the actual thing that physicists care about is Hilbert spaces, because according to them, the universe satisfies something called reflection positivity. So reflection positivity says that if I flip the incoming boundary onto outgoing and outgoing into incoming, And I also change this geometric structure. Let's say if it was a conformal structure, I take the opposite of that, then this linear map that I assign should become the adjoint of the map. So if I flip incoming and outgoing and change this geometric structure into its opposite, then this map should become the adjoint of the maps. So there is unitarity or reflection positivity. Okay. So now I can first say I want to be derived or infinity 1. So vec was a 1 category. What if I want to just remember it to be 1 category but kind of keep track of homotopies? What you get is the category of chain complexes. Also chains appear a lot in quantum field theories, especially if you have like operators that have derived behavior, like cohomological field theories. So what should be the category to put here? So this is open. We do not have a candidate for the version of chains that is continuous in the sense of Hilbert spaces and unitary or dagger. So we don't know what this is. But now let's say we can't do infinity. So we come back to trying to do 2. So 2-vect is a category which needs to have some objects, some 1 morphisms, and some 2 morphisms. Yeah. CH is chains and homotopies. So chain complexes and homotopies. So this is kind of the canonical infinity 1 linear category. Okay, so here I want him. It turns out this is a question that we can answer. So first, let me try to tell you what 2-vect is. So a model for 2-vect is algebras, bimodules, and bimodule maps. So this is called the Morita category of alg. So this is a 2 category, and it turns out that this is a good candidate to be 2-vec. So what is the unitary version of this? So what is 2-Hill? So it turns out 2-Hill should be von Neumann algebras. 1 morphisms are bimodules again. And 2 morphisms are bimodule maps. So let me try to tell you a little more about this. So what is the composition in this category? Suppose I have algebra A and B. I have bimodules H, which is a BA bimodule, and K, which is an AC bimodule. I can take the tensor product over A. This is the composition. And what is the identity? A, which is a module over itself. This is the identity for this. And bimodule maps are HBA to H prime BA. So these are BA linear maps, which are the 2 morphisms. In the von Neumann algebra world, it turns out you can define these tensors by universal properties. In the von Neumann algebra world, things are a little tricky. So von Neumann algebras are function analytic algebras. So they're double commutant closed algebras. So they're star subalgebras of bounded linear maps on some Hilbert space, sorry, such that double commutant is equal to A. So this is some Hilbert space. Okay. So let's say one-Neumann algebras R and R prime, and bimodules again H, R prime R, and K R double prime. It turns out that things are not so easy here. So if you want to fuse bimodules, if you get composition, here this process is called consfusion by Ellen Kohn, and it is a Hilbert space completion of the tensor product. So you have to do some Hilbert space completion. And in the same spirit, R is not a bimodule over itself because R is not a Hilbert space. An algebra had an underlying vector space, and these were just vector spaces with that action. So this was acting on itself, whereas R is not a Hilbert space. So you have to do some completion of it, which is called the L2 space or the standard form. And now R becomes an RR bimodule. So this is the unit or identity one morphism. So you already see that when we try to add unitarity, the tensor product, the identity things already change. So two morphisms are still fine. So if I have map from, if H is a Hilbert space with R prime actions, I can take the R prime linear maps. So this is okay, but this and this are broken. So now you can try to play this game further and further and ask, what if I want to have 3 vect and 3 Hilb? Because infinity we have no idea, but now you can try to do one step at a time. So again, 3 vect is understood in some sense of the word understood. So the 3 category which people use is tenscat, or the Morita category of tensor categories. So objects are tensor categories. So for people who don't know, tensor categories are just C linear monoidal categories. One morphisms are modules. So let's say I have C prime. One morphisms are modules. So M is now a category with actions of C and C prime. This action is given in terms of a functor. Two morphisms are equivariant maps. So C prime linear functors, and 3 morphisms are natural transformations. Okay, so 3 vect is understood, and 3 Hilb. So this is what people call categorified von Neumann algebras. So if you want to think of a tensor category as a categorified algebra, well, how do you see that? You go to the linear category, like you go to the category of linear categories and then look for algebra objects in it, and you will get tensor categories. And these are in some sense functional analytic tensor categories. And then there is this entire thing about developing the fusion. So here, yeah, almost the last thing. So here there is a tensor product that you can do, which is called the lean tensor for categories. This has been developed, but you want to develop the same kind of machinery for that you know from tensor categories for these function analytic tensor categories. And so one of the things that I do is develop this thing called 3-hill, and then we can go further, hopefully. But I'll finish here. So in the conclusion, I would like to say that you can either go about building these cubordism categories and generalizing them. So for example, adding defects here, adding more kinds of geometric structures and studying the cubordism side of the things. You can try to develop higher algebraic targets or function analytic higher targets, or you can try to construct examples of those things from, you can try to construct examples that physicists care about. So you can actually say, okay, I'm going to write Chern-Simons theory as that functor. So there are like 3 kind of parallel research directions that happen in functorial field theory. But I will stop here. Thank you so much.
Thanks very much for your nice talk. Are there questions, comments?
Yeah.
Thanks a lot. Very, very nice.
Thank you.
Usually when you go to higher category,
Yeah.
There's an inclusion of n2, n+1 categories in the sense that you add homotopes on the existing morphism. Is it still true here? Because already you're going from vect to 2-vect.
So, yes, so one important thing, let me write it here. So the way that, so what we want to say, what the thing that n-vect should satisfy is that endomorphisms of the monoidal unit, let's say endomorphisms in n-vect of the monoidal unit should be n-1 vect. So let's test this example. Endomorphisms in 2-vect for the monoidal unit, which is just the algebra C. This should be vect. So what are bimodules over C? They are vector spaces and linear maps. So in general, the thing that we want to satisfy is that, so some people would also write loops at 1 of n-vect. So higher algebraic categories are sort of de-looping vect. So you have vect at the top, and then you de-loop, 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 and then you have generalized it. So this is an iterative thing. And I could also say end in 3-vect. So the monoidal unit in tenscat is vect. And it turns out that this is the 2 category of linear categories or the Morita category of algebras. So the endomorphisms of 3-vect of this monoidal unit is a 2 category. And then I can look for the monoidal unit in here and then get vect. So this is like de-looping. In that sense, they embed. But you're right that there is also, I can sort of have the trivial 2 morphisms. I can put vect, at least in cubordisms, I can just say that I have, so n-1. I can include this by saying that the top level things, everything is in ISO. But yeah, so there are these 2 ways to relate n-1 and n. There's also this thing, like you can make the top levels isomorphisms, and that would give you like the stupid 1 level up category in some sense.
Thank you for your very nice talk. Maybe my question is related. You mentioned at some point that going to higher categories enabled you to see points as local objects.
Yeah.
are there several levels of locality that you're introducing? And if so, in what way?
So this locality is most apparent in TQFTs. So what I said was that we are chopping our space-time more and more, all the way up to points. And in TQFTs, it turns out that what I assign to the point under this functor fully determines the theory, which is this big theorem called cobordism hypothesis. It was a sketch of it, like Byers and Dolan first conjectured it in 90s, and then Lurie proved some version of it or sketched the proof in maybe 2009 or something. So locality in that sense is saying that for topological quantum field theories, everything is determined by what I assign to the point. Like, it doesn't matter what the topology of spacetime is. If you know what to assign to the point, you can make an assignment to the spacetime. In that sense, topological quantum field theories are fully local, but we don't have any such statement for quantum field theories. So it might be true that quantum field theories have some level of locality that you can determine what happens on the spacetime if you know, let's say, some level of the data. In topological field theories, you have full locality, but maybe in other quantum field theories, you have some other sort of truncated kind of locality. Yeah.
So maybe this is a naive doubt, but there, when you define the transition amplitude from boundary to boundary, it looks like it is talking about scattering and all, but is it what you're talking about, or?
So if this thing had no boundary, then I want to assign the partition function.
Okay.
And in physics, if you're just doing a QFT, in the way physicists do it, you would give some boundary conditions on this boundary and some boundary conditions on this boundary, and then evaluate that. And then it would give you the scattering amplitude. Like,
Yes.
so in that sense, I like to call it transition amplitude. Some people like to call it evolution or something like that. But what you have to remember is that if you fix the boundary conditions, then you should again recover something which is a number.
Okay, but how will you define free theories here, like free QFTs?
What do you mean free?
Free QFTs.
Like free boson, free fermion.
Yes, yes.
So that they are the examples that are very easy to do. So for that, you will just give this Hilbert space or vector space for your theory, and then this is like free theories are actually examples that you can construct in this language. So I don't know what the
No, but like there, that will be a trivial transition amplitude. That's what you're saying.
in
Free theory.
I think what you mean by trivial and what I mean by trivial is different.
Okay.
Like, what I mean by trivial would be that this is identity, and that's not the case.
Oh, okay.
So I guess if you wanted, I mean, here, if you had a non-trivial manifold,
Yeah.
then there is, even though it's not even if it's a
Free
non-interacting scalar field, there's an effect of the geometry somehow,
Yeah.
right? So it's, so that comes into play, perhaps that's the way.
Okay.
Like when you do the path like when you calculate the partition function, you will still have to integrate, and the topology and geometry of this will still affect what the value is. So when you say trivial, what I would assume that this is always identity, and that's not true for free theories.
Okay, yeah, right.
Okay, so this is maybe slightly more technical question, but you mentioned at some point the Lorentzian attempts to talk about functorial theories. And so you were probably thinking of this work of Schenkel, maybe.
Exactly.
Yeah. So have you thought about that? I mean, that's great work, but I think one could do a bit more. So have you thought about like higher generalization of that and try to think of this maybe like a functor into something like
Function
involving
analytic.
higher Hilbert spaces and
Yeah.
von Neumann algebras and so on? Do you think it's possible?
So the thing that I currently work on is 2D chiral CFTs, and they land in those targets. But somehow, and what I do is I construct functorial 2D chiral CFTs from conformal nets, and conformal nets are inherently Lorentzian.
Yeah.
But somehow there's some hidden Wick rotation happening.
Yeah.
So I still end up using Euclidean cobordisms.
I guess that's probably specific to D, right? So,
yeah,
so
exactly.
The problem is actually to generalize it to higher dimensions. Because,
I think setting up the cobordism category should not be that difficult, especially if you want to do infinity n, because in that you will just say, I want this geometric structure to be whatever Lorentzian. And then the way you set up the category is just by introducing cut grids. So that can be done. And then if you land in higher Hilbert spaces, then in principle you can capture QFTs, but I don't know what example to try it with. So maybe we can talk about that. Like maybe there's some baby example that we can construct, and then that way we can exploit the full potential of function analytic targets.
Thank you.
Oh, Schenkel, SCH. Yeah.
And
Yeah, and other people, but
yeah.
these two are the main.
So these people do higher versions of algebraic quantum field theory. Yes. Yeah. The paper which you could read for this is called "What is an elliptic object?" So this is the conjecture that sort of laid the groundwork for building function analytic targets, because here you genuinely want QFTs. So Witten, Atiyah, and Graham initiated the trend of thought, but then for like more than a decade or more than 15 years, people were only focusing on topological quantum field theories, because it turns out that if you have infinite dimensional space of states, then people did not know what to do. And now if you are doing these function analytic categories, you can still have infinite dimensional spaces and you can still do things. But after they sort of conceptualized functorial framework, most of the work was only for TQFTs for a long, long time.
Okay. So in the interest of keeping to a schedule, maybe we will stop here and you can take more questions in the breaks. We will have a very short break now and start again at 1:15 sharp. I won't wait for latecomers. So yeah, let's thank Nivedita again.